Okay, so for this lecture, we'll be talking about the quantum mechanical particle in a box. Um, and I'd like to preface, before we get into setting up the problem and solving it, I'd like to talk a little bit about where we're going with this and put things in perspective a little bit, preface this with a little bit of perspective. So the particle in a box is kind of like an ideal gas law. It's kind of a simple system that we can look at quantum mechanically. It's a good starting point for understanding more complex systems. We can start with particle in a box and then, layer on more complexity later. This is often the way that problems are handled in a lot of physics-related fields, where you try to strip away as many details as you can initially, and then start sort of layering to get down to the root of the problem, and then make some conclusions, and then maybe start to layer on some more complexity after that. So this is a simple system. It's just a particle inside a box, basically. Okay, so another thing related to ideal gas law, it turns out that the ideal gas law, the statistical mechanics derivation of the ideal gas law typically starts from the quantum mechanical particle in a box, from the three-dimensional particle in a box. We'll start off with the 1D case and then move on to 3D. Another thing to think about the particle in a box is that this quantum system illustrates a lot of the key features and phenomena in quantum mechanics. We derive wave functions which correspond to states of the system. We have to normalize these wave functions. We see that the wave functions are orthogonal, or we get to test that concept that we brought up previously. And we also end up with something that we haven't talked about yet, which is quantum numbers that are assigned to the various states of the system. These are usually integer numbers. Sometimes they're half integer. Similarly, there end up being a quantized or discrete set of energy levels. So their energy has very well-defined values for a given system. And another issue is we'll bring in the 2D case and the 3D case, and this brings up a couple of important concepts. One is separation of variables, which is kind of a mathematical approach to solving multi-dimensional partial differential equations. And we'll also see a concept called degeneracy, which is having different states with the same energy level. And so this is an important concept in quantum, and it's related to, say, the Aufbau type principle that you've seen in general chemistry, and so so we start to see that concept coming in, and sort of see where it's coming from. That's the nice thing about starting with a simple system. We can sort of see that that degeneracy is related with the dimensionality of a system, which is a interesting and perhaps useful concept. Another thing we'll see, we'll have an illustration of Heisenberg's uncertainty principle for this system, and so So those are some things to watch out for, kind of give you an overview of where we're headed with this. And of course, we're going to apply this as a model, as a simplified model for more complex systems. And we're going to take a physics approach, okay? So it's worthwhile talking a little bit about what the approach is, why we're doing things the way they are. This is a way of breaking down a physics problem that may seem somewhat familiar based on some of your other physics courses. And initially we start off with some kind of diagram where we enumerate what particles or other bodies are in the system. We also look at things like maybe charge of various particles, other properties, the mass of the particles, and we assign a set of coordinates. Okay, so our diagram helps define those coordinates, and we may have to refer back to it because certain aspects of the problem may require considering what the coordinates are. And the coordinates, of course, then allows us, once we have coordinates, we can set up forces as a function of the coordinates and or the potential energy. They're somewhat interchangeable. You can go from force to potential energy and from potential energy to force. Force is the gradient of the potential. Then we look at the problem and consider what is moving and therefore has kinetic energy. So we'll have to take into account kinetic energy in our system, because then once we have kinetic energy, potential energy, we set up our equations. In this case, we set up the Schrodinger equation, which has kinetic energy and potential energy terms. But then we solve that equation to get energy levels and wave functions. And then perhaps we follow up with looking at various properties of the system, in addition to energy, other things like position, momentum, the spread in position and momentum, perhaps other properties related to those. And then we make some conclusions, right? We try to make sense out of what we just worked through, because it's not purely a calculation exercise. We're trying to use math and physics to make predictions. Okay, and of course that may involve comparison to experiment. And sometimes that's an iterative process. Sometimes you get to the experimental results and there's a discrepancy, and the discrepancy leads you to maybe some aspect of the problem that was overlooked in the initial setup, and so there's kind of an iterative process. Okay, so without further ado, let's go ahead and follow this process. We're going to first set up our diagram. We have a particle inside a box, and so we set up our box and we set up our coordinates, x equals 0 and x equals a. So we have a box of width a. Okay, there's nothing magical about a. It's just what we give to the size of the box. And I have these vertical arrows because I'm sort of plotting energy along the y-axis here, in that this represents the potential. And the potential is 0 inside the box, and then it spikes up to infinity at the edges. So there's no forces there's no potential inside the box, so potential is 0. And then at the edge, we want an infinite barrier so that we keep our particle inside the box. It turns out that's an important aspect of the particle in a box. So we have some box, can't let the particle escape from the box, therefore we have to set up an infinite potential barrier at the edges of the box that essentially, if the particle tries to go outside the box, it experiences an infinite force returning it to the box. But that infinite force is only incident over a tiny infinitesimal region, and therefore, so it doesn't accelerate the particle. It just bounces it back, basically. The same way, you know, if you have a ball of some sort, a classical particle or ball inside a box, it's just going to bounce off the edges. It's not going to pick up additional kinetic energy from the walls. Okay, so we have infinite wall, and let's see, we have a particle of mass m, and it can move, a particle of mass m, and it can move inside the box. Okay, and then let's just be a little bit more explicit about what the potential is. The potential is 0 in the region from 0 is less than equal to x is less than equal to a. And it turns out that the less than or equal doesn't end up mattering. You can also say just less than. And that it's equal to, it doesn't really affect the results. And we say that the potential is infinite everywhere else. Okay, so that so we can be sure that it stays inside the box. Okay, so now that we have the potential defined, we have a particle that's moving with a mass that has a mass m, and so there's a kinetic energy term, and you may recall that the kinetic energy operator is minus h bar squared over 2m, where m is the mass of whatever is moving, right? Not say the mass of the box, right? It's the mass of the particle. And d squared dx squared. In other words, that's p squared over 2m, where the p is the momentum operator minus I h bar d dx. That's for momentum along the x-axis. There's only one axis here. This is a 1D problem at this point. Okay, so then our Schrodinger equation, so since inside the box v equals 0, so then the Schrodinger equation inside the box is just minus h bar squared over 2m d squared dx squared. So let's say d squared psi dx squared plus 0, so we just won't, the potential is 0, we won't add a term for that, and then equals E psi, right? So we have H psi equals E psi, where H is the sum of the kinetic energy and the potential energy terms. And we don't have a potential energy, so we just have the kinetic energy, so we have this, this second order differential equation. Okay, and then there's a bunch of sort of constants or scalar values, and we can kind of lump them together. So let's define k equals square root of 2 times the mass times the energy over h bar. Okay, if we do that definition, then that allows us to sort of simplify our Schrodinger equation, and we can write it as d squared psi dx squared is equal to minus k squared psi. In other words, in sort of typical differential equations type notation, we say psi double prime is equal to minus k squared psi. Okay, and this is a fairly straightforward differential equation. What we have to do is that we have to find some function psi. Maybe we'll find more than one, in which case we may have to do some additional steps to figure out which one is the proper one. And that may involve the boundary condition. So this ends up being a boundary value problem. Because we have some restrictions at the edge of the box, which we'll see in a little bit. Okay, so then basically solving this differential equation is to find a solution such that, is to find a function such that when you take the second derivative of the function, you get minus k squared times the function you started with. So it's easy to think of some functions that do that have this kind of repeating quality, that when you take the second derivative, you get back some constant times the function you started with. However, there's also this minus sign here, right? So we have to find functions that will give you some sort of minus sign. So we know that dx of sine x equals is cosine x, and we know that dx of cosine x is minus sine x. Aha, so maybe our wave function is say sine or cosine. So either of these, if we take the derivative twice, we get back the function that we started with and a minus sign. And if we also include the constant k inside our trigonometric function, sine or cosine, then we're going to get this constant k squared, right? In that d dx sine kx is k cosine kx, and so on. So you'll get your k squared. So that's so possible trial solutions are, first of all, we don't know exactly, is there some sort of constant out front. You know, the size of the wave function may matter, so we're going to generalize and include a constant out front, and then say sine kx. That will work. That will solve the Schrodinger equation, at least inside the box. Cosine kx, that will also work. There are also some other possibilities now. E to the kx won't work because it doesn't give you the minus sign, but if you have a complex exponential, say e to the I kx, that will work. Take the derivative one time, you get a ik. Take the derivative the second time, you get I squared, k squared, and times ae to the ikx. And so I squared gives you the -1. And similarly, e to the minus ikx will work. However, not all of these, so these are trial functions. And then the question is, can we narrow it down? Are they all valid? Well, we haven't really solved the whole problem yet, right? We need to consider the edges. So if we look at the edges, now this is a little tricky, but because we're playing with infinities here, so we have to sort of take what we get with what our conclusions are with a grain of salt, and try to make sure we don't introduce some additional assumptions or violate conservation of energy somewhere or something like that. So at the edges, the potential is infinity. So we get minus h bar squared over 2m d squared psi dx squared plus infinity times psi equals e psi. Okay, so we expect that the second derivative, which is related to the curvature of the wave function, we expect that to be finite, particularly for these trial functions, right? Those don't have any infinite second derivatives. And we expect that our energy of our system will be finite. Otherwise, sort of all bets are off. So then the question is, how do we get sort of finite on the right-hand side, when on the left-hand side you have infinity times some function? And of course, this is just at the edges, so this is at x equals 0 and a. We can, and outside the box, this only works if we require psi equals 0 at the edges and outside our box. Okay, so that helps us deal with this this apparent problem. Okay, so and that is consistent with if we have if we go back to our physical picture, we have the edges are walls, so we don't expect there to be probability density at the wall or just past the wall, and because probability density that's related to wave function squared. Yeah, probability density, if there's probability density outside the box, then it's not a particle in a box. Okay, so it makes sense. So we can either use this argument or just based on going back to our physical picture to state that the wave function has to vanish at the edges of the box. Okay, so then that eliminates some of these probabilities. Out of this list of functions, which of those functions is 0 at x equals 0? Only this one, psi equals a sine kx. is going to be equal to 0 at the edge at the x equals 0 part of the box. Okay, so now we've imposed one boundary, and that's told us which of those trial functions we can use. Now we impose the second boundary at x equals a. That's going to give us additional information. So we also have that a times sine, where a is just some constant that we haven't determined yet, is equal to 0 at x equals a. And so we have, in order for this to be true, then we know that sine is a periodic function, and that it goes through zeros at sine pi equals 0, 2 pi, 3 pi, and so on. So therefore, we end up with an additional condition which says that k, the product of ka, where a is the length of the box, has to be equal to some integer multiple of pi. Okay, and I'm not including n equals 0 as a possibility. That works. That makes sure that your wave function vanishes at the edge of the box. But it also would make the wave function vanish everywhere. If n is equal to 0, then k would have to be equal to 0. And for k equals 0, that gives you just sine of 0 as your wave function, sine of 0 times x. And that works mathematically, but as is often the case, math can give you sort of two solutions, only one of which is usable. For instance, an analogy is you can imagine setting up some algebraic, some problem related to equilibrium constants, and you end up with some expression, end up with a quadratic equation, and one of the solutions to the quadratic equation gives you a sort of a negative concentration for one of your reagents. And of course, in chemistry, negative concentrations, you can have changes in concentration that can be negative, but an absolute concentration can't be negative. So therefore, you throw out one of the two solutions out of the quadratic equation. It doesn't mean that math is wrong. It just means that you have to look at your results and compare to the physical picture, and sometimes you can eliminate one of the two solutions or one of several solutions based on looking back at your diagram and your definitions, and that's one of the reasons why we have a diagram in the first place. But anyway, so we don't just blindly follow the algebra because that solves part of the problem, but not the whole problem. We also have to consider the physical picture. So the physical picture tells us then that that n has to be some positive integer, positive non-zero integer, 1, 2, 3, or so on. And so then we can of course rearrange this, and this says that k has only certain values, n pi over a, where n equals 1, 2, 3. Okay, and then we can substitute that back into our wave function. We'll say psi sub n is equal to a sine n pi x over a. where again n is equal to 1, 2, and 3. Or we can say kx over a, either one. Sometimes one might be more useful than the other. We can just say a sine kx over a, and then just define k using that expression. Either one. Okay, so then now let's, so now that we have found a set of wave functions that are solutions to the Schrodinger equation and that obey the boundary conditions, now let's move on to energy or energy levels. So we take our wave function, plug it into the Schrodinger equation, differentiate, and we should get a set of energy eigenvalues that correspond to the state psi sub n, where psi sub n is a wave function that represents some state. So we end up solving, in this case, minus h bar squared over 2m d squared psi. We're back to the middle of the box. We use the edges to sort of quantize our system. We used our edges to impose some conditions on the system. Now we go back to solving inside the box. That's the most important part. And that's where energy and so on is well defined. So we get minus h bar squared over 2m d squared psi dx squared equals e psi, or psi sub n. And when we take the second derivative of the wave function, right, we end up with h bar squared. Okay, the minus cancels, right? And so we get h bar squared, k squared over 2m. So the h bar squared and the 2m, those were there already. The minus k squared comes from taking the second derivative of psi. And then we end up with the psi. Right, when we take the second derivative, we get back the function times minus k squared. Okay, so then essentially we have this set of constants or parameters on the left-hand side, and then we have energy on the right-hand side. So then we say that E is equal to h bar squared k squared over 2m. And now we can plug in our, this will be E sub n because k also depends on n, and it's n pi over a. So plugging that in, we get En, energy is a function of n, where it turns out n we'll call a quantum number. And it's just a fairly general term that we use to describe an integer index, sometimes half integer, that describes a state or a wave function. So our plugging things in, we get n squared, h bar squared, pi squared over 2m a squared. Now there's a little bit of simplification that we can do, because h bar is h over 2 pi, and we have that pi squared. So anytime we have like a product of, say, pi squared times h bar squared, we might want to switch to h and do some cancellation. So then, of course, that's going to give you an extra factor of 4 in the denominator, and we end up with n squared h squared, not h bar. It's tempting to put the slash back in. The pi's cancel over 8m a squared. Where n is the quantum number. So essentially we end up with this ladder of energy levels. They're not evenly spaced, so it's a perhaps poorly constructed ladder or a quadratic ladder of energy levels. Now let's let's move on to something a related concept, which is an energy level diagram. So first of all, the n equals 1 state is going to be h squared over 8m a squared, where m is the mass of the particle, a is the size of the box. So that's interesting. The size of the box ends up in the denominator and it's squared. So we'll have to think about that a little bit. Let's so that's for n equals 1. For n equals 2, we're going to get 4 h squared over 8m a squared. So that's going to be 4 times energy of n equals 1. The energy for n equals 3 is going to be 9 times the energy of n equals 1. And one way we like to represent these is in an energy level diagram. Now, the utility of this is not obvious at first glance. But this is a term that I'll be using. There'll be multiple kinds of diagrams, okay? And there'll be multiple diagrams that might have energy somewhere in them. So this is a particular type of diagram where we're looking at energy levels. It's not the potential energy diagram, which might be, say, a plot of the potential energy function. It's, you know, so this is a specific concept that I want you to learn as a sort of key concept or vocabulary item, and that's the concept of an energy level diagram. For an energy level diagram, we set up energy along the y-axis, and we use a set of short horizontal lines to represent the energy levels. And then we might say put quantum number information in there as well. And we might also put some information about the energy levels. Let's say E1, we'll drop the n equals, we'll just call it E1, is h squared over 8m a squared. Then we'll say E2 is equal to 4 E1, E3 equals 9 E1, and so on. And I didn't get the spacing exactly right here, but basically you would end up with a spacing between these rungs on this ladder. Between 1 and 2, we'd have a difference of 3 E1. Between n equals 2 and n equals 3, we have a difference of 5 times E1. So the spacing between the rungs on the ladder goes up. So this is an energy level diagram. Okay. If I ask you for an energy level diagram on a test or on a quiz, I don't want to see a potential energy function. I don't want to see how kinetic energy varies quadratically with velocity. That is a diagram that has energy, but energy level diagram has a fairly specific meaning where you end up with these short horizontal lines that represent energy levels, and they're oriented with energy increasing along the sort of y-axis. And these end up being important because a lot of times we're interested in transitions between energy levels in spectroscopy. And so the difference in energy between the rungs on this ladder are important, and it's useful to have a diagram to help guide you. Another issue is that sometimes you will have actually, so this is one particle in a box. What if we have multiple particles in a box and different particles are at different energy levels? Then we can include occupancy. And you've seen in electronic structure diagrams of atoms or molecular orbital diagrams of molecules, those are types of energy level diagrams. Okay, so there are specific cases of this more general concept of an energy level diagram. Anyway, so that's a good. Let me note a couple of final things, and then we'll move on to some other issues. So a couple of interesting things to notice. One is that the lowest energy in the system is not zero. Okay, so if we put a classical particle in a box, just put a tennis ball in a shoebox or something like that, its lowest energy would be zero. It would be tennis ball at rest inside the shoebox. It seems like this quantum mechanical particle is never fully at rest. In fact, it has some kinetic energy associated with it, even at absolute zero temperature. So there is what's called a confinement energy, or a 0-point energy. 0-point energy is more associated with vibrations, but you can use 0-point energy in this context. Anyways, they're two closely related concepts. So there's an energy associated with confinement in that if A is some number, if A, the size of the box, is some number that's not infinite, then the lowest available energy level is h squared over 8ma squared. Now in practice, for A is larger than a few nanometers, the energy is going to be negligible and would correspond to temperatures of millikelvin, that sort of thing. So now that said, a lot of quantum systems are somewhat confined. You can think of an atom inside a lattice as being sort of confined and by the other atoms that are there sort of holding it in place. And so it's going to have some confinement energy or some 0-point energy associated with it. And this is one of the sort of strange quantum mechanical predictions, which is that particles always have some kinetic energy associated with them, and then therefore we can think of them as always having some kinetic energy. And this has been experimentally confirmed in a lot of different ways. We'll talk about them more later. So that's a point of divergence if you're trying to compare and contrast with regular F equals ma Newtonian mechanics. This is one of the key differences. Okay, and for the next lecture, we'll look at wave functions, normalizing, and orthogonality and expectation values.